welcome to Honors Pre-Calculus. We're going to talk about the graphs of what the book's referring to as the other trig functions, which are the trig functions that are not sines and cosines, namely tangent, cotangent, cosecant, and secant. And you'll notice on all four of these examples, all four of these trig functions, we have some asymptotes which sine and cosine did not have, and that's because sine and cosine both have r as their denominator, x on r, and r always is a positive value, so we're never dividing by 0, where tangent, cotangent, secant, cosecant do not have denominators of r, they have denominators of x and y. So let's get started. Tangent, we know that tangent is the ratio of y to x. If we go back and visit our unit circle, at this point right here, 0 degree rotation or 0 radian rotation, we have the point 1, 0. So y on x, 0 on 1 is 0. And as we, let me zoom out here just a little bit, and as we move around the circle, it's worth for tangent stopping at a 45 degree angle or pi on 4, where on the unit circle we all know that's middle length over middle length, root 2 on 2, root 2 on 2. If you haven't seen my video on unit circle gold, it's worth looking up. We have a very, very easy way to come up with, not really even memorizing these, but a process to come up with these angles very quickly. So at 45 degrees, and it's not shown on this graph, we have y on x, root square root of 2 on square root of 2 on 2 over square root of 2 on 2 just becomes 1. So at pi on 4, we're actually at 1, and that's definitely worth noting. And then when we get to 90 degrees or pi on 2, we have a problem because this is the point 0, 1, and y on x is 1 on 0, and that's undefined, and therefore pi on 2, we have an asymptote. Let's circle backwards pi on 4. Here we would be to the right square root of 2 on 2, but down square root of 2 on 2. And at that point, we see that our y on x ratio is, this is not a negative, is negative square root of 2 on 2 over square root of 2 on 2. It's negative 1. And we have a point here. So negative pi on 4 gets us to negative 1. And then negative pi on 2 gets us to the point 0, negative 1, which y on x is also undefined. So there's a nicely contained period of the tangent graph. Notice it's always increasing, but its period is only pi, and that has a lot to do with, we've talked about quadrant 1, all, quadrant 2, students, quadrant 3, take, and quadrant 4, calculus, being all trig functions are positive here, sine is positive here, tangent's positive here, cosine's positive here. So tangent's negative, goes positive, negative, positive, negative. In other words, it repeats its process of positive, negative every 180 degrees or every pi units. So our defining values on the graph of tangent, I don't start at 0. I like starting at negative pi on 2. And we get defining values. Can I squeeze those in here? Negative pi on 2, undefined. Negative pi on 4, negative 1. 0, 0. Pi on 4, 1. And pi on 2, undefined. You could go from 0 to pi. It just, I like having everything contained between the two asymptotes. Okay, now let's consider cotangent just for a moment here. Cotangent, as I start rotating around, cotangent is the ratio x on y, and x on y at this point is undefined. Therefore, we've got an asymptote at 0. At 45 degrees, x on y is 1. So notice both tangent and cotangent contain that same point. Definitely worth noting that we'll always be at pi on 4, 1 with cotangent and tangent. It's just cotangent is a decreasing function. As we move to here, x on y, 0 on 1 is 0. And then as we move, let's move on to this point, which would correspond to 3/4 pi, this is negative square root of 2 on 2, square root of 2 on 2, writing a little smaller for whatever reason, and x on y there would be, as you can see, negative 1. Before we get around to this point at negative 1, 0, where x on y is negative 1 on 0, undefined. So our defining points here for cotangent, I would use 0, undefined, pi on 4, 1, which again is coincidental with tangent at pi on 4, pi on 2, 0, 3/4 pi, negative 1, and pi undefined. Okay, now cosecant and secant, we can really build off of sine and cosine graphs. If you look at the graph of sine would fit, sine of x would fit right in here. And you can almost visualize, or probably can visualize, that reciprocal property going on. Take a look. When sine is 0, the reciprocal of 0, let's say 0 on 1, is 1 on 0 undefined. So when sine of 0 is 0, so the reciprocal of that undefined. Sine of pi is 0, undefined. We can see it, 0, undefined. Sine of pi on 2 is 1. And the reciprocal of 1 is 1. Now along the way, somewhere along here, sine hits 1/2. And at that point, that would be, and of course that's 30 degrees or pi on 6, but at that point we're up at 2. Somewhere along here it hits 1/10. And at that point we're up 10. So we get this nice little shape that just fits like puzzle pieces in with sine, and secant is the reciprocal of cosine, and here's the cosine graph. Looks like this. And once again, we have that reciprocal of 0 is undefined, reciprocal of 1 is 1, reciprocal of negative 1 is negative 1. Somewhere along here we hit a half, reciprocal of a negative 1/2. Somewhere along here we hit it, a reciprocal of negative 1/2, negative 2, and so on. So it just fits really, really nicely. So when I'm graphing cosecant or secant graphs, I'm really kind of thinking about sine and cosine and the defining values that go with that. So for cosecant, our defining values, I go 0, undefined, pi on 2 would get us up to 1. Pi, undefined, 3/2 pi gets us down to negative 1. And 2 pi gets us back to undefined. And you'll see as I do these, I don't even worry about remembering these because I've got sine and cosine, and I'll handle secant when we get to that as well. Okay, so things to note, the range, negative infinity to infinity for tangent. The period is just pi. That's unique to tangent and cotangent. The others are all 2 pi. And they go ahead and tell us that the domain can be everything except for pi on 2, and add multiples of pi, integer multiples of pi to that. So we can go forward pi, so pi on 2, forward pi, backward pi. That's where all the asymptotes are. Likewise, the asymptotes on cotangent occur at just plain old multiples of pi. 0 pi, 1 pi, 2 pi, negative 1 pi, etc. And very, very similar discussions for cosecant, secant. Notice the range is affected here. The range can only be from negative infinity to negative 1. There's always a no man's land in between here. We can't be between negative 1 and 1. Same for secant. Okay, let's get started. Find the x-intercepts of the function. So A, the x-intercepts. Well, here's one right here, and that occurs, it appears at pi on 2. But then there's another one, pi later, and another one pi before, and another one pi before that, and I'll bet there's another one pi after that. So plus multiples of pi. Find the y-intercepts. Well, the y-intercept B is an asymptote. So there are none. Let's go C here. C, find the intervals on the graph which f of x is increasing and the intervals where it's decreasing. Well, this graph is only decreasing, but it's not always decreasing because it jumps from here up to here over the asymptote. So I'm going to talk about this interval right here. It's decreasing from 0, not including 0, until we get to pi, not including pi, but that would be 0 to pi, but also we could add to that a whole nother multiple of pi. It starts over every multiple of pi, so plus n pi plus n pi. That would be a way of writing it. Decreasing. There is no decreasing. So D, find all relative extrema. We don't have any relative maxes or mins. It's going to approach infinity and going to approach negative infinity. None. And E, find all vertical asymptotes, if any. Well, we have vertical asymptotes at 0 and pi later and pi later and pi later. So that could be 0 plus n pi, or of course just n pi. Okay, number 8. A, find any x-intercepts. None. B, find any y-intercepts. Nope, don't have one here either. Asymptote. Let's go C. Find the intervals of increase. Okay, it's increasing. I'm going to go from here to this asymptote, and that appears to be pi on 2. Whoops, sorry. Pi on 2, going to leave a blank. And it's increasing until we get to pi, and then it's increasing. This is 2 pi from here to here. It's increasing here as well. It's also increasing here as well, but take a look at these two. They're 2 pi apart, so that's plus 2n pi plus 2n pi, and I should state this is where it's increasing. In union with, it's also increasing here and there. And notice this is pi units away. So I could actually come back to this and say, I could talk about these separately with plus 2n pi's, because this is 2 pi away from there. But I could also say, take a look. It's, well, wait a minute, increasing. That is not correct, what I was about to say. Increasing and then decreasing. So let's see. This is negative pi to negative pi on 2, and then that happens 2 pi later. So I don't have a nice even increment. See, it's increasing, increasing, and then I got a long gap where it's decreasing, then it's increasing, increasing. So plus 2n pi's plus 2n pi. And decreasing, I'm going to leave that to the viewer, but it will be along the same lines as what we're doing here. And find all vertical asymptotes. We got a vertical asymptote at 0, at pi, at 2 pi. Oh, that's E. That's part E, sorry. Find all vertical asymptotes at 0, at pi, at 2 pi. So it's every pi, so just n pi. And D, the extremes. Here's a relative minimum, relative maximum, relative minimum, relative maximum. It's the smallest point in its neighborhood. It's the largest in its neighborhood. And those are occurring every pi units, but starting at pi on 2. So pi on 2 plus n pi. Okay, let's get down to the graphing of these. Now, I'm going to stamp these things just to give you a feel for what the stamp looks like. Again, I'm remembering that tangent, the graph of tangent, always goes through pi on 4. Let's call this pi right here. Always goes through pi on 4, 1, tangent and cotangent. This is y equals tangent. Since tangent is y on x, remember we've got to point out here 1, 0. Y on x is 0 on 1, that is 0. And that tells me what I need to know. Our graph looks like this. Okay, but this point's pivotal for us because that's our cotangent starter as well. So this graph is just 3 times as tall as that. So all it would change would be this point would be up 3. But I'm going to go ahead and stamp this and go through this process. So we would choose a value for x, we'd multiply it by 3, and then we just take the tangent and we're done. I just want to kind of reiterate those defining values. The values we really want to put into tangent would be negative pi on 2, negative pi on 4, 0, pi on 4, and pi on 2. Tangent of 0 is 0, or excuse me, is undefined. Tangent of negative pi on 2 is undefined. Tangent of negative pi on 4 is negative 1. Tangent of 0 is 0. Tangent of pi on 4 is 1, and tangent of pi on 2 is undefined. And here, did I say 3 times as tall? This would actually be 3 times as fast. I'm doing this early in the morning, but apologies for that. In reverse, we need to divide by 3 or multiply by 1/3, and we get, let's see, my smallest denominator is going to be 12th. I would get a negative, or my biggest denominator is going to be 12th. I'd get a negative pi on 12. This would be negative pi on 6, or negative 2/12 pi. Here's 0. Here's 4/12. 1/12 pi. Shouldn't do it this early in the morning. And 1/6 pi, or 2/12 pi. So if we're going to graph this, we would count clearly by pi on 12s. 1/12, 2/12, so I might put a pi on 6 here. Negative 1/12, negative 2/12, a negative pi on 6 here. Everything's happening 3 times as fast. We have a point at negative, or a value at negative 2/12 of undefined. At positive 2/12, undefined. At negative pi on 12, negative 1. And at pi on 12, positive 1, and at 0, 0. So it looks sort of like a cubic. I will tell you, these do not truly level off like a cubic. It doesn't really come out of their level. It really goes through there with a slope of about 1. There's our curve, and we know that we could build additional off of that if the need be. Yes, I'd need 3 in there. 1, 2, 3. We can build additional portions of the graph off of that, additional periods. Okay, cotangent graph, and you can certainly go through and find all the periods based on material we've done before, the period, increment, the amplitude. Amplitude, not such a good word to be using with tangent. In this case, the period's 3 times as fast, 2/3 pi. Our increments were pi on 12, just divide by 4. There was no vertical shift, there was no phase shift. All right, cotangent. So I'm going to go ahead and stamp this thing. We're going to choose a value for x. We're going to multiply pi. We're going to take cotangent. We're going to multiply by 3. And perhaps we could do this one conceptually as well. Everything happens pi times as fast. The normal period for pi, for cotangent, is pi. So pi times as fast, pi divided by pi 1. The increment would be 1/4 then. The amplitude, if there was such a thing, we'd talk about the 3 here. It's 3 times as tall, but still it goes up to infinity, down to infinity. No vertical shift, no phase shift. Everything just happens pi times as fast, and we're 3 times as tall. So cotangent, if we go back and visit cotangent at 0, this is 1, 0, is x on y undefined. And remember, both at pi on 4 go through 1. And truthfully, that's all I need to know if I know the shape of the graphs. And here we'd be over it. This is a rotational curve. I'm doing a lot of things kind of silly this morning. But let's go over and look at the graph of cotangent from that. At 0, we would be At 0, we would be x on y, 1 on 0, undefined. At pi on 4, we would be up 1. At pi on 2, we would be down here, and then we would go to our down phase, and then finally, by pi, we would get our asymptote. Okay, so our defining values, the values after we multiply pi, is what I'm trying to get at, are this should be 0, pi on 4, pi on 2, 3/4 pi, and pi, where cotangent goes between asymptotes from 1 to 0 to -1. And now we get undefined 3, 0, -3, undefined, and upward we divide pi, and we just get 0, 1/4, 1/2, 3/4, and 1. So the graph we're looking at, this is plain old y equals cotangent. The graph we're looking at goes from 0, let's see, 1/4, 2/4, 3/4, 1, just plain old 1. Between these asymptotes, pi on 4 gets us up 3, 1/2, or 1 on 4. 1 on 4 gets us up 3. 1/2 gets us to 0. 3/4 gets us to -3. And there's our curve. Kind of a nice, I'll get some additional, there's some extra wiggling going on in some of these. Kind of a nice target is just to aim about halfway between this point and the center line. Come out of there aimed at that and then curve down through. Okay, secant. Going to be thinking about cosine. Cosine graph, I think I will do this one just conceptually. I'm going to just think about the cosine graph, and here's cosine, first period of cosine. Looks like this by 2 pi. It looks like that. So 1/4 cosine, because we got a 1/4 here, this would just be up to 1/4. And if I have that curve, these points, let's go ahead and do our real graph that we're dealing with here. I'm going to go 1/4, -1/4. Let's see, pi on 2 pi, 3/2 pi, 2 pi. This point still exists. This point still exists. This point up here exists on the secant graph. But these zeros, these centerline points, become asymptotes. And my curve fits in there. And that's a full period. If I went to -pi on 4, I could add another asymptote. If I went another 1/4 of a pi to 2 1/4 pi here, we could add another asymptote. And there's our curve. Okay, and then finally, let's go ahead and do some where we're going to actually do some stamping with secant and cosecant. So here we're going to choose a value for pi, or for x. We're going to multiply by pi. We're going to take the secant, and we're going to multiply by 1/4. The values I want to go in secant are just like the values I want to go in cosine. 0, pi on 2, pi, 3/2 pi, and 2 pi. So now is where I'm just thinking cosine. Cosine of 0 is 1. Cosine of pi on 2 is 0. The reciprocal of 0 is undefined. Cosine of pi is -1. Reciprocal of -1 is -1. Cosine of 3/2 pi is 0. Reciprocal, undefined. And cosine of 2 pi, we're back to 1. Multiply those by 1/4. Undefined, -1/4, undefined, and 1/4. And now divide away pi. 0, 1/2, 1, 3/2, 2. And we can see here our period is 2 pi if you want it. Our is just 2, sorry. Our increment is 1/2. Our amplitude, if we were going to talk about amplitude, we'd be mentioning something to do with the 1/4. Vertical shift, no vertical shift at all. phase shift, no phase shift. I don't move right or left. Things happen faster and things are a little bit shorter. So let's go ahead and graph this. I'm going to count just 1/2, 1, 1 1/2, 2, plain old 2. 0 is 1/4. 1/2 is undefined. 1 is negative 1/4. 3/2 is undefined. And 2 is 1/4. And we just it's not correct to call these parabolas. They're not parabolas, but they have an appearance like a parabola for a little bit. So that's more than a period, and we got the y-axis. And here's one that without a doubt I would stamp. So here we go. We're going to choose a value for x, multiply 2, subtract pi, take the cosecant, which I'm going to be thinking about sine, and multiply that by 1/2. The values I want to send into cosecant, just like sine, just like cosine, 0 pi on 2, pi, 3/2 pi, and 2 pi. And sine goes from 0 to 1 to 0 to negative 1 to 0. So the reciprocal of 0, undefined, reciprocal of 1, reciprocal of 0, reciprocal of negative 1, and reciprocal of 0 times 1/2. Plus pi, let's see, that's going to be pi, 3/2 pi, 2 pi, 5/2 pi, adding a pi, 3 pi. And then I'm going to multiply by 1/2 or divide 2. And I notice I'm going to get, when I do this one, I'm going to get 3/4 pi. Here I'd get 1/2 pi or 2/4 pi. Pi, 5/4 pi, 3/2 or 6/4 pi. So 2/4, 3/4, 4/4, 5/4, 6/4. I'm going to make tick marks by 1/4 pi's. I'm not going to put a tick mark here and just immediately call it 2/4 pi. That's 1/4, 2/4, 3/4 pi, 5/4, 6/4, 7/4, 2 pi. Okay, I need up to 1/2. I need down to negative 1/2. At 2/4, not here, but at 2/4 pi, we have an asymptote. At 3/4 pi, we're at 1/2. At pi, we have an asymptote. And that really tells me everything I need to know. I know I'm going to come over here and put this one in. There it is, 6/4 pi. And I know at 5/4 pi I'm going to be down on the opposite side. There's a full period, but you have to build back to the y-axis. We could add another one in here. We could draw these all day if you like. But I have to get back to the y-axis, excuse me, error number 10. And that, of course, would be right here. More than enough. Okay. So, hope that's helpful. Apologize for some errors along the way. Perhaps the video I'll be redoing, but at this time I'm pretty pressed for time. So, there's your assignment. Please notice all of these are being done by hand, even though in the assignment the book is going to say some of these should be done calculator. They would say this should be done calculator, but they just don't know how smart you guys are. And I do. I know we can do these by hand. Okay, hope that's helpful. Please let me know if I can be of any help.